Okay, I'd like to invite everybody to grab a copy of the review packet that I have just dropped in the chat. Let's see. We will get started momentarily. For right now, though, I want you guys to look at that 21 Fall Math 112B review packet. That is the document we'll be using to guide our discussion this evening. All right, I'm going to give everybody about 3 more minutes to join, and then we'll get started. So to have a copy of this available, just go to the chat and you should see the file there. If you don't see it, feel free to message me or unmute yourself and speak out. This session is being recorded, and I will send out the link to the YouTube video once the session has concluded and the video has finished processing. All right, everybody is still joining us. If you have just joined us, then you'll want to grab a copy of the review packet, which I have just dropped into the chat. If you are dialing in, you can follow along on the screen. If you can somehow email me at lisa.blue@eku.edu, I can email you a copy of this. Once our session has concluded, I will send the annotated version of our review packet out, as well as the video recording. All right, I'm going to give everybody about 1 more minute to get logged in, and then we'll start. So while we're waiting, please look through that packet and consider questions you'd like to see answered tonight.
Hello.
Hi, how are you this evening?
I have a question. I'm good, thank you. I would prefer if I could figure out how to get the Zoom meeting on my laptop, but it's telling me that I need like an authorization, or I'm not authorized, or I need like a email and password.
Okay.
How do I go about?
If you sit tight just 1 second, I will drop that information into the chat. And if you can grab that and carry that over to your laptop, or
That is the thing. I called, like I couldn't figure out how to do it, and they said an alternate way would be to call in. So like I'm in like a call on my cell phone, and I can't see like the screen or the chat or anything.
Right. Do you have access to your email?
My EKU email?
Yes.
Yeah.
Okay. What is your email address?
It's Devin, DEVIN.
Okay.
_ Foster.
Okay. Give me just a second. Oh, there you are. Okay, I found it. Okay, so you'll want to log into Zoom. And let me see if I can get the quick and easy version copied over to you. You'll just use your EKU credentials to log in.
Okay.
Okay, I just sent you the link.
Okay, I appreciate it.
Hey, sure thing. Okay. All right. Has everyone else been able to open up the review packet that we'll be using tonight? Okay, fantastic. Then we're going to go ahead and get started. So what I have for you tonight is a set of midterm exam review questions, and I picked them according to these student learning outcomes. So we'll talk about those in just a second. Your exam, this midterm, will cover chapters 4 and 5, as I have listed here, but they do not explicitly cover these algebra toolbox sections. These algebra toolbox sections represent fundamental pieces of information that you need to have a good grasp of before you move on to the new content. I have included it here because I want you guys to see the student learning outcomes. Now, what are these student learning outcomes? Student learning outcomes are like a contract between you and the textbook author, and that they're telling you exactly what level of understanding you need to be able to have to be successful in the course. And so if you're asked to give an exponential decay formula, okay, we would call that the lowest level of Bloom's taxonomy. So that shouldn't be too stressful of a question to answer. But then if we want to understand it and use it or apply it, that's usually our word problems, okay? And so we can see that these are going to increase in difficulty all the way up until you're creating such as a capstone course type of an assignment, all right? So usually we stay somewhere between remember and analyze as far as coursework is concerned at this level. And so using these learning outcomes, I want you to use them to ask yourself these questions in order. First of all, do I recognize all the terms in the question? If the question is talking about a logarithm, you know what a log is. What does it do? What's its purpose? Do I understand what the question is asking me to do? If you don't, then go back, make sure you understand all the terms and read the textbook until you look at the example problems and you can go, okay, I kind of see what's going on here and how they're doing this. All right. And then what I have done for you with these packets, can I find examples of questions that match this learning outcome? That's what I've done here for you so that you can begin to look at the learning outcomes, which I found in my math lab and some of the supplementary material. And then I grabbed textbook questions. So notice here, all these questions we're going to look at this evening are directly out of your textbook. So if they're an odd numbered question, you will have those answers in the back of your textbook. All right. Once we get past 3, then we say, can I answer the question? All right. And then once you've answered the question, can you then check your work? Can you look at that answer and say, yeah, that makes sense, or no, that's not a great answer. All right. So those are student learning outcomes. So an example here. So our chapter 4 algebra toolbox, which we're not going to go over in depth. This one asks us to identify the domain and range of a given type of function. So that is the learning outcome that was given for this section. That's one of several learning outcomes. I've also gone through and grabbed some of the textbook notes. All right, so these notes are screen captures of your textbook because I'm hoping that you'll take the process that I've used here and model this in your own studies in the future. All right, so we will not go over the chapter 4 algebra toolbox questions explicitly. All right, awkward pauses mean I'm adding people to the chat. And so if you have just joined us, make sure that you have a copy of this review packet in front of you. The review packet has been dropped into the chat. All right. It looks like I've got everybody on board. And so I'm going to, all right, so this is more of our algebra toolbox. So we're going to start here with section 4.1, transformation of graphs and symmetry. I do have 2 individuals here from the math department that are going to take over this portion of the discussion. And so they will be guiding you through the rest of this material. What we'll do is we'll look at each individual learning outcome, and then they will ask you, are there any of these problems that you need to see worked? Okay. Keep in mind, there are 55 pages of content that we're presenting tonight. Obviously, we won't get through it all, but if we pick and choose what looks like the scariest sets of problems, then we should be in good shape. All right, you guys ready? Okay, let's do this. I'm going to turn it over. Cheers.
All right, so we're operating off the theory that everybody can hear me. My name's Ben. You might be in one of my 112 and 111 classes. The first thing we're going to start out with is graph transformations and symmetry. I'm going to assume that everybody knows how to graph a graph in general, right? We know what an x squared would look like. We know that an x cubed, has this nice little cubic function, right? So what we want to really look at is there's 4 major things that are going to change how a graph looks. First off, we have our vertical shift. Vertical shift, like it says, it's going straight up or straight down. So we have this fancy little notation here, a graph g of x equals f of x plus k. It sounds kind of crazy, but if we look at our example exercise over here, if we just treat, the first one as your standard f of x and the second one as a g of x, we can kind of see that, hey, we're just taking this original f of x and we're making this shift plus 5, right? All right, so does anybody have any questions about the vertical shifts? Any question numbers that you want to look at that look a little intimidating? Okay, doesn't look like we have any questions. What about horizontal shifts of graph? Shifts that take place inside of the little parentheses around the X. Anyone have any questions about this? All right, just remember, whenever we're looking at these, fight your intuition where it says, X minus H, a lot of people want to try to travel left with that. Make sure that we're following the rules, right? X minus H is going to take us in the positive direction.
All right, so if there are no questions over 1 through 13, we're going to move on. Take a look now at questions 14 through 24. Are there any of those that you would like to see worked? If you change your mind, feel free to drop that in the chat. Otherwise, we're going to keep clicking on through here. So last call. Any questions 14 through 24? All right, so 14 and 23, circle those. And 19, okay. You may need to drop stickies.
Yes, dropping stickies, that's the plus sign, right?
Mm-hmm.
Stickies. Ooh, that's big.
Mm-hmm. And then, there you go.
All right. So starting off with this number 14 here, we can see that we're starting off with the cubic function, this f of x equals x cubed. What we're doing to it is we are modifying it by a factor of 0.4. Remember that if your compression or stretch is between 0 and 1, that is going to be defined as a compression and it's going to get shorter and stubbier. So what we're actually doing, we're taking a cubic function that looks something like this 0.4, it's going to kind of stretch it out. So it's going to be less steep, right? Let's see if I can move my stickies. All right. So where we took this, this A value between 0 and 1, and we draw a little graph in here. Looks something like this. It is now kind of horizontally stretched, if you want to think about that, or vertically compressed. Does that make any sense for number 14? All right, next, let's look at number 19. It says the suppose the graph of y equals x to the 3 halves is shifted to the left 4 units. Hiding people. There you go. All right, so sorry, we got a little bit of echo here. All right, so whenever we have these functions, y equals 3 to, or x to the 1/2 or x to the 3 halves, we can write that in the exponential or the square root form. So remember, x to the 1/2 is the same as the square root of x. What we have here, we are taking this power, this 3 halves power, and we are shifting it to the left 4 units. Remember when we said that we're going to fight our intuition? A lot of times, you think, hey, we're moving to the left, we're going to use a minus sign. Well, we're actually going to be using a +4, right? So what happens is we're just going to take the parent graph to the y equals x to the 3 halves, and we're just putting it in parentheses, put that 4, the positive 4 attached to it, and then we apply the entire exponent to that. Just make sure that we don't try shifting that in the wrong direction. Ooh, fancy. This iPad's a new toy. I'm still learning it. All right, now moving on to 23. Sticky. All right, so this one's going to combine both the vertical and horizontal shifts. Whenever we have our function, right,
Finger off the sticky.
Aha, magic. So we start out with our parent graph, y equals x. We're going to be shifting it up 3 units and left 6 units. Remember, anytime we do something horizontally, we can kind of think of it being in parentheses attached to the x, right? So it says we're shifting left 6 units. We're actually going to use an addition sign. And anytime we do something vertically, this 3 units up, that's going to go outside on its own, right? So we want to apply the shift to the x function directly, any exponents or whatever. Once we get that value, then it's going to be shifted up from there. Does that make sense? All right, if there's no more questions, we can go ahead and move on. We just people talking. Just slightly awkward talking to the screen. Thank you. All right. One thing I do want to point out at the bottom of this page here, if I can move the sticky note back. Aha. So we have these symmetry questions here. We encounter this a lot in the tutoring center. Remember that if something is symmetric to the y-axis, we call that an even function. And whenever we apply a negative to the x value, it's still going to come out to the same as if we applied it, if we had just taken the function with respect to a positive x, right? So if we apply the f of negative x, we still get the same value as if it was just a positive x. With respect to the origin, we see that those xy points also have a negative x, negative y point. We call these odd functions. We encounter a whole lot of these problems on the consultations this past diagnostic test. So make sure we're looking at these. We can test for an odd function if we put that negative x in. And instead of getting our normal value back, we're actually getting the negative version of it. And then, of course, with respect to the x-axis, at the top of this next page here, we actually see things like, they're a little sticky on here. Okay, the sticky's fine. All right, does anyone have any questions about these? Okay. All right, so let's go ahead and jump on down to the next page. Okay, explain the even function. Yeah, let me get back up here. My little sticky note that I'm tagging along. So that's when we have that symmetry across the y-axis. No, I drew on the page. So if we have something like a parabola, y equals x squared, what we're seeing here is if we were to put in an x value, say 2 here, we're going to get this value here. If we put in the value -2, we're going to get the same value, and they're both going to be positive. That's what's happening with this negative sign here. It's disappearing, if you want to think of it that way, because the function is going to be symmetric across this particular axis here. Did that clear it up at all? Okay. All right. And then, of course, if it's not symmetric across any of those, then we just say it's not symmetric.
All right, so how about those next two learning outcomes? Identify transformations from equations and write an equation of a transform function from its graph. You guys need to see any of those questions worked out.
Second one.
All right, very good. Thank you.
All right, so set number 27 here. Remember to use my little sticky notes. All right, so 27, what we're looking at, which one? 28. Okay. Let's see. All right, so these are actually work out to be pretty similar. Just different shaped graphs to start with. What we're looking at with this first one is f of x equals square root of x reflected across the x-axis and shifted 2 units up. Remember, when we have these words written out and we're trying to put that into an equation, we want to treat it with the order of operations, right? So in order for something to be reflected, let's see, square root of x, right? In order for it to be reflected across the x-axis, we need the negative version of this, right? So it starts out looking like this on a graph. We actually want it to be reflected down here, right? So this guy goes down here. So we're going to reflect it first, and then we're going to shift it up by 2 units. So our end result is going to look something like this. And as far as that number 28, instead of shifting it up or down, we're just going to be shifting it right 1 unit, which that's going to stick underneath of the root part of the equation.
That's what that makes sense.
Did that make sense? Yes. Okay. Does everyone understand how to write the equation from a transform function of a graph? No. So this particular question is kind of incorporating all the ideas that we had from above. We can see right off the bat that it is been reflected over the x-axis and shifted up by 2. So right off the bat, we can see that we start with our parent function y equals x squared. It hasn't shifted left or right, it's only up and down, and it's reflected. So we have this negative x squared plus 2, right? Because it's reflecting first and then being shifted up. Let's see. And down 4, yeah. And then it's not being stretched or compressed, and we can test for that using the vertex form of a parabola. That make sense? Yep. A few more examples of these transformations, if you guys. Fair enough. All right, so these, obviously we're not going to be able to go through all of these, but you'll be able to go through. If you have any questions afterwards, you can always feel free to come down to the tutoring center. We can go spend more time one-on-one with these. When we start looking at determine symmetry visually, it's exactly what it sounds like. We look at it, we say, hey, look, this graph here is symmetric on both sides with regards to the y. This one's the x and the y, so on and so forth. These tend to be a little bit easier for people to wrap their heads around. Does anyone have any questions about this? Scrolling. Would 36 be symmetric? So 36, we actually see when we're talking about symmetry, we're only concerning ourselves with if it's symmetric about y, x, or the origin. This particular one would not be symmetric about the y, obviously not about the x because there's nothing down here, and it's not symmetric about the origin either. Determine if this symmetry, if function is an absolute value. So and when we're looking at these absolute value ones, like number 35, it's kind of like an absolute value, but it's been turned sideways. We can see that it's going to be symmetric across this x-axis here. The standard absolute value, it was an awful graph there. Standard absolute value, if it hasn't been shifted left or right, it's going to appear to be symmetric across the y-axis. If it's been shifted left or right, then we get it offset, kind of like number 30. Let's see which one number 36 was, where it's not going to be symmetric at all. That help? Okay. Determine symmetry using a table of ordered pairs. These are going to follow just like our rules up here for these symmetries, where we have this, x comma y, we get the point negative x, negative y. You'll be able to just look through here and follow those along. Does anyone need to go over those?
Yes.
What we do?
Or is that?
That was an old yes.
Okay.
So we've been going. Zoomed. We've been doing a lot of these symmetries in these even and odd functions. Remember, even, odd, or neither, those are all going to be based off of our rules that we just went above. Does anybody have any questions about these type of problems? Number 43. Mm-hmm. All right, so
You don't have to throw a sticky down every time you write, just if you need to cover something else.
oh yeah, I'm definitely gonna have to use a lot of stickies to do that. That's a cool toy. All right, so let's see. Determine algebraically whether the graph is equation is symmetric with respect to x, y, or origin confirmed graphically. So we can see that our parent graph for this function would be y equals 1 over x, right? For people who aren't familiar with what these actually look like, it's going to be something like this on one side and this on the other, right? So starting off, what we're trying to confirm with, right? We can kind of already go ahead and see that it's gonna be like symmetric across this origin, but finding it algebraically, this is one of the ones where we can test a few different points. We throw in our x values, and we can make just like a little make just like a quick little XY chart. If we pick x equals 6, then our y is going to equal 1. If we pick x equals -6, our y is going to equal -1. And we can see that it's going to be symmetric across origin, and that's how we would check it graphically, or algebraically, and then we would confirm it by graphing it out on our TI-84s. Does that make sense? And we would just do this same process for these other ones. We can always use our little rules. F of x equals, or f of -x equals f of x to show that it's even. If it's even, it's going to be symmetric across the y-axis. If we get our f of -x equals -f of x, that's going to be odd. That's going to be symmetric across the origin, so on and so forth. If it doesn't fit into either of those, then it's neither. It's not going to be symmetric across either or. Is there any other questions about that? 44, 41. And yeah, these are going to follow the same rules. Let's see. Down, out of the way. If we were to just glance at 40 real quick. So our f of x, -x squared plus 4. If we were to plug in f of -x, well, we're going to get a -x squared plus 4. Well, when we square this -x, it's just going to come out to a positive x, but we still have this minus sign out front following our order operations, right? So we're still going to end up with a -x squared. Nothing's changed with this plus 4. So what happens is we get this negative f of x, or this f of -x is going to be equal to negative f of x. So we can go ahead and see that that's going to be a odd function. Or, excuse me, sorry. F of -x equals positive f of x, which is what we expect with an even function. Sorry about that. Got old people eyes, can't see my own writing. Did that help clear it up as far as algebraic solutions to this? Let's see. And this is going to be similar to what we did above when we're trying to determine if they're symmetric across the different axes. Wherein, hey, if it's even, it's going to be symmetric across the y-axis. If it's odd, it's going to be symmetric across the origin, so on and so forth. Did we need to go over any more of those? So is everyone starting to feel comfortable with these transformations? Do we want to move on to the next section? So, and again, I know we're kind of restricted to time here, but you guys can always come down to the tutoring center with these packets, or, you know, we have copies of them we can keep up there, and we can go through additional problems if you want to work one-on-one.
Speed it up just a little bit because we're not going to get the logs.
All right, so does anybody have questions about how we compose the functions? No questions? All right. We have some more function composition stuff here. Does anybody have any questions about how these are done? Any problems you want to go over? Which problem would you like? 21? All right, so anytime I see these expressions here, this f of g of x, I just go ahead and write that as f of g of x. And what this allows me to do is I'm able to just write, you know, f of x, f of g of x as f of all this stuff that g of x is, and then plug that directly into the f function, right? Instead of sitting there trying to solve each one individually, we can wrap it all up together. And we can see that our f of x function is 2 times all this stuff that is our new quote unquote x value. So this is how I prefer to do it. Are there any questions about how I went through and did this? So these are the ones that are all going to follow the same type of process, where we, you know, write this f of g of x or g of f of x, and we're just going to try to substitute in the entire thing as the new x value, if you want to think of it that way, for the f function. And for g of f of x, it would just be the reverse x value. Does that make sense? Here we're just combining all these functions together using the different operations. Any other questions?
I got a question.
Yes.
So if it says like something like f minus g of x, are you taking like f, like the individual, like the value of f of x and like g of x, and you're putting them in parentheses and then subtracting?
So something like this, right? G minus f of whatever. See if I can find a better example. I cannot. Yeah, so here we're looking for f minus g of x. We just look at number 1 here. What we're doing is we're going to take that first, you know, f minus g. We're going to take that f, and then we're going to subtract off the entirety of the g of x equation. A lot of people will just write minus 4 minus x, and they don't distribute this negative sign to both. So we remember to subtract off the entire other function, not just the first term. Is that what you were asking?
Yeah.
Okay, yeah, we definitely want to subtract off that entire term, not just or that entire function, not just the first term. All right, so do we want to go ahead and move on to the next section now? Is there any other questions about these composite functions? I know we have a lot more pages to get through here. All right, moving down to 4.3, one-to-one and inverse functions. Do we have any specific questions about this? Determining whether functions are inverses, so on and so forth.
Try to go one whole page at a time.
There is a whole page at a time, but I keep forgetting that.
Yep.
All right. So,
One.
all right. So the next little section here is one-to-one functions. Does anyone have questions about that? Using the horizontal line test. Hey, there it is. What about finding the inverse of a function? Do we have questions about that? Number 19. That might be just sticking out now. It'll work right. All right, so when we go to write the inverse of a function, there's several steps that will always work. We got this f of x equals 3x minus 4. First thing we do, we change the f of x to a y. Then we want to swap the variables. So we're keeping all the numbers the same. We're just literally swapping the letters. Now we're going to solve for our y, adding 4 to both sides and dividing by 3. Gets us this y. And then we want to rename that f inverse of x, right? So these steps will always work as long as your function is one-to-one, which you definitely want to check as you're going through this process. And then once you get this function back, if you plug this into your original f of x, if you get back x as a result, then you know it is correct and it is an inverse to that function.
You've only got time for one of those.
Yeah.
So
How do you check for one-to-one on a written function?
On a written function. So there's pretty much anytime you have an even function, something like a parabola, x squared, x to the fourth, something like that, they're pretty much always going to fail this horizontal line test. Any odd powered functions, well, most odd powered functions will pass it. The exceptions being when we have these nice little turns here, the cubic function. So those you'll have to check using your tables or graphing it out. Yeah.
move on.
Graph inverse functions. So so many screens.
Yep.
All right.
Any last questions?
Any last questions about these inverses? All right, we're about halfway through on time, so we're going to jump down to the next chapter, and Gavin's going to take over.
All right, so while they're trading places, we are going to skip the algebra toolbox. Okay, so if you have trouble with any of that, please let them know. And we're going to start off with section 5.1 on exponential functions.
All right. Hello, my name is Gavin. Ben's lucky he got the easy chapter, so I'm going to apologize in advance. We're going to suffer through this together. First things first, we're just working on identifying exponential functions. Does anyone have any questions on 1 or 2? Okay. All right, what about any questions on graphing exponential functions? The good thing about these is most of these you can just put in your calculator. All right. What about transformations? Does anyone have any trouble with transforming exponential functions? They do follow most of the same rules as the other ones, just a little bit more complicated. Okay. If I'm going too fast, feel free to ask me to go back. I won't be upset about that. This is still transformations. Do any of these look like anything anyone would want to work through? Okay. All right.
18.
Oh, 18. All right. Okay. So 18 kind of falls in this awkward category because we're playing this matching game. Everything from 13 through 18, we're matching between graphs A through F. So this is going to take just a second, but let's see. So we're working with, okay, you all said y'all were okay on graphing exponential functions. So I'm going to assume, sorry, I know this is ugly, that you all know the graph for y equals f to the x will look something like this, something along those lines. So if our graph, our new equation is 4 to the x minus 2 plus 4, looking at this table up here, what kind of transformations might we have? Well, it looks like we're going to have some sort of horizontal shift and a vertical shift. And that's going to be it. So a vertical shift comes from comes from this on the outside. So this is going to be up 4. And then we have a horizontal shift where if we're subtracting, then we move 2 units to the right. So looking at this, we're going to know that our graph should be slightly moved to the right, and our starting when I'm sorry, whoops, I don't know how to erase on here, but when x, is that the right thing?
That's not right.
Oh,
Right
whoops.
there, there's the eraser.
Okay,
go.
there we go, yeah. When x equals 0, then we should get something like this, vor to the 0 minus 2 plus 4. Oh, this is looking ugly. I don't want to do this one. I don't like that we, yeah, we're going to change that a little bit. We're going to try and figure out where we can make our exponent equal 0. And so that's just going to be when x equals 2. Because then 4 to the 2 minus 2 plus 4 is just 4 to the 0 plus 4. And does anyone know what anything to the 0 power is? I shouldn't ask. That's going to take too long to respond. But anything to the 0 power is just 1 plus 4. So at x equals 2, we should be getting something about 5. Oh, thanks, Araya. Close enough. So we're just going to look over here, see one that's not with a vertical asymptote right around, not 1, but 5, or sorry, not 0, but 4. So we're going to look for one that's not getting close to the x-axis. And actually, I could have made this a lot simpler. Since we have a vertical shift upwards of 4, we just find the one that looks like it's moved away from the x-axis. So, and is moved 2 units to the right. So, you know, all of these look like they're generally looking pretty similar, but this one looks like it's been moved out to the right. So I would say that's probably worth noting. This one looks like it's been moved up, but it still doesn't look like it's been moved to the right, but this one fits both of the categories. So for 18, the correct answer would be D. I remember you were right, I know. All right, does that make sense? I know I went on a really long-winded tangent there, but I hope that makes some semblance of sense. All right, I'm just gonna move on to the next page. Okay. Again, does transforming graphs of exponential, oh, sorry guys, yeah, I know that's really zoomed out. Transformations of exponential functions, does that sound like anything y'all might need help on, or how are we feeling about that? Okay, I'm gonna go ahead and move on. Now, what about the differences between exponential growth and exponential decay? Do any of these questions look like something y'all might want to work on? Don't worry, if you don't have any questions now, I'm sure we'll get there when we get to logs. Okay. Oh man, that's really ugly. Yeah, I figured. So the first thing I would recommend, they give us a specific domain. So if you really want to work through this and get the entire graph, whoops, you could start at -5 and work your way all the way up to 15. I'm not going to go through all that. I don't know why I started at 12 either, but there we go. And then you would just plug them into the equation f of x. And we could do that. That would take a while. So
Do F of 10.
do f of 10.
Uh-huh.
Okay, we'll just do, oh, for b, we'll just do, we'll work on b. If you want this quickly, you could put this into your calculator into y equals, press second graph, and you could bring up your entire table, by the way, just throwing that out there. I thought that might help a little bit. We'll do specifically f of 10 because that's question b. And so that means we're going to do 12e to the -0.2 times 10. And 0.2 times 10 is just 2, but it's a -0.2, so it's going to be 12e to the -2. And I believe that gets us an ugly number. It's really just 12 over e squared. Sorry, I'm putting it in my calculator, as you should do with things involving e. And if we wanted an approximate answer, we'd get something like 1.624. I don't know. It doesn't really say anything about rounding, but generally about 3 decimal places isn't a bad place to go. Does that make sense? Okay. Does anyone have any other questions about anything on this page? Because this is when things start to get a little complicated. All right, I'm going to go ahead and move on. Okay, more of that. All right, here's the good stuff, guys. We have any questions on any of these log questions? Anything on the screen? Okay. All right.
So do one from each section.
Yeah, okay. So what I'm going to do is I saw number 4 first. So I'm going to start with number 4. Yeah, okay, I can do that. So there's a general rule. Let's see if they have it written down. It actually, oh yeah, I do. Okay, I see it right here for part or questions 1 through 4. What we're trying to do is go from here to here. Okay, so it's already in log form. And the easiest way that I can think to do this is, while looking at this, define what b is equal to, meaning your base, your y is equal to, meaning the thing that the log is equal to, and then x, which is the thing inside of the log. Lucky for us, this one is pretty straightforward. Y is equal to y, x is equal to -x. And it's a log where they don't specify what the base is, so that means it's a base of 10. All right, and we just want to rewrite that into exponential form, which is just x equal by. So now we just plug in these in here. So x is just -x. Our base is 10, and then our y is y. And that would be the correct answer for number 4. Does that make sense? Oh, okay. Devin, does that definition of natural log make sense? Okay. All right, and for the sake of time, I'm going to go ahead and move on to questions 5 through 8, and it looks like number 8 was the first one requested there. Okay, so we're going to work this one backwards, but I'm going to do the same exact thing. I'm going to start with this form, x equals by. So I'm going to go ahead and define each term. X is the thing on the opposite side of the equal sign from the exponent. So I know this is going to get really confusing, guys, and I'm really sorry, but defining everything, x equals y. Our base equals 9. And then our exponent, y, is equal to 2x. Okay. And then we just turn that into form y equals log b of x, where we just plug in these terms into that. So our, whoops, we said our x is, oh God, I'm sorry, I've already confused myself. Oh, hello, I don't know how I did that. Is it this? Yeah,
Yep,
we're
there you
there.
go.
Okay, oh, I really screwed this up somehow. Let's see how this goes. All right, so y was equal to 2x. Ooh, now it looks all thin. I don't know how I did that. We'll play with that in a second. Our base is just 9, and then x was equal to y. So let me rewrite this so it looks a little bit cleaner, but 2x equals log base 9 of y. And oops, there we go. Okay, and that should be your answer. Does that make sense? Okay. All right, any other questions on this page before I move on? Because I know we cover a lot more when we get to the basic properties of logarithms. Okay, I'm going to go ahead and move on. Okay. All right. Oof, okay. Again, any questions on the properties of logarithms or then graphing the logarithms? When it comes to graphing logarithms, I definitely recommend your calculator more so than trying to do by hand. Of course, you can create a data table and plot from there, but I definitely recommend using calculator. And you said number 26, so I'll start with that one because I saw that one first. Okay, so we're going to use the properties of logarithms to evaluate the expression. So we've got
Zoom or.
I'm going to rewrite it. Yeah, I was going to rewrite it. So we've got 6. Whoops. Sorry, guys. I'm not used to drawing on like this fancy technology, so just having a hard time. 6 to the log base. Oh, to the log base 6 of 25. Well, there's a fancy rule here. Let's see if we can point it out. Rule number 4. If our bases match, then what ends up happening with our exponent? What gets left behind? What's our final answer? It's going to be 25. It's just going to be the log will cancel out with our base, and it just leaves behind what was within the log. Does that make sense on number 26? I'm going to assume yes. I know I'm great at this, so I know you guys are really getting it. That same exact rule is what we used for number 25, by the way, also. So the answer for number 25, since the base is the same, would just be 12. All right, any other questions on this page? Okay, I'm going to go ahead and move on. All right. Whew. Inverses of exponential functions and rewriting logs. Do we have any questions on this page? Looks like 19 was first, but they're from different sections, so that works. I'm going to do 19 and 31. All right, so for 19a, we're going to find the inverse of y equals 4 to the x. And the first step always when trying to find an inverse is just to swap x and y. Okay, and then the key, this is actually a chance where we get to use a logarithmic rule we used earlier, where we changed it to exponential form. So we've got it in exponential form. So we're going to go from b to the y equals x to y equals log base b of x. So we're just going to use this rule again. Okay, so we're going to clearly define everything here. So our b is equal to 4, y is equal to y, x is equal to x. And then we're just going to plug those into this equation. So y equals log base 4 of x. And that would be our inverse there. Then you could just graph it in your calculator. And I believe what you end up getting, let me double check before I say something weird. They should look something like this to each other. That's not right. 1 second. They're going to have asymptotes to where they never actually like cross, but something like that. Does that make sense for number 19? Okay, I'm gonna move on to number 31, and then I'll probably do 32 also because 2 people asked for it. So 31 as a sum or difference, okay? So we're starting out with natural log. Sorry, I recommend with every single problem, rewriting it. It just gives your brain a second to, figure out what all is going on there. There is a log rule, and let's see if we have it here. It's number 7 right here. If within your log, within the parentheses, there is division, you just turn it into a subtraction problem with 2 separate logs. So this is just going to break down into a natural log with our numerator minus a natural log with our denominator. And that would be it for number 31. All right, and now I'm going to do number 32. Or try to, I should say. All right, so we've got log base, or sorry, not log base. It's just log of x cubed times 3x minus 4 to the 5th, all in those parentheses. All right, so this one, we've got multiplication within the parentheses. So that means we're going to use this one right here, rule number 6. So if you have multiplication within the parentheses, you break it into 2 separate logs connected by addition. Okay, so this is going to look something like this in our next step. Whoops. Okay, log of x cubed plus log of 3x minus 4 to the 5th. Okay, but we're not quite done. We got one last step, and that is if you have exponents within logs, you can bring them out front of the log. So what it really is log multiplication. So you're just going to do 3 log x plus 5 log to the 3 or log of 3x minus 4. And that would be your final answer there. Oops. Do those questions make sense? Okay, awesome. All right. Now this stuff starts getting a little insane. We're going to start on the Richter scale and everything. Does anybody want to work? Oh, these aren't even those questions yet. Does anyone want to look at either 39, 45, or 46? $45. Okay. Sorry, give me a second to read through it. So we're given an equation, 27.4 plus 5.02 natural log of x. All right. And they want where x is the number of years from 1960. So that means in 1960, x equals 0. That's important. I see that's something that a lot of people struggle with when they come to the tutoring center, is defining what x should be. So it says, what does the model predict the percent to be in 2011 and in 2015? Well, in 2011, x would just be 2011 minus 1960, which I believe is 51. So that means we're just going to plug in 51 into x. So y equals 27.4 plus 5.02 natural log of 51, which once you plug that ugly thing into your calculator, you get 47.138. Okay. And that would be in the year 2011. For 2015, you would just do 2015 minus 1960. So you'd just be plugging in x equals 55. Does that make sense? Okay, cool. All right. Does anyone want to go over any of these questions? It's okay if you don't, I won't be upset. $61. Okay. I don't know. Have you all covered the Richter scale at all in your 112 classes? I'm just curious. Or on your 111 homework in either one? Okay.
I used to do it 105, but they
Yeah.
cut it out.
Okay.
This formula for intensity.
Yeah, I see this. This is a real mess of a problem, guys. I'll be honest. You're going to get to watch me struggle here for just a minute. Okay. Wait a second. Okay, so it looks like for this one, we're just going to use rule number 3. If the difference of the Richter scale measurements of 2 earthquakes is the positive number d, the intensity of the larger earthquake is 10 to the d times that of the smaller earthquake. Okay, so we have one, I don't know how to really label this, but we've got, I'll just say R1 equals 9.0, and then R2 equals 6.8. I just did R1 as 9 because that's the bigger one. All right, and so then all we have to do is find the difference between them, 9.0 minus 6.8, and that's just 2.2. And that means that R1, or the, I'll put it specifically like this, the 2011 earthquake was 10 to the 2.2, which is specifically a really ugly number, 158.489 times more intense than 2018 or 2008. Does that make sense? I think that's really I don't, does that make sense?
Times the I got you. Intensity of a larger earthquake is this times that of this one. Okay, got it.
Okay, so does that make sense? I know that was kind of an on the, I just learned that, I'll be honest, but all right.
See anything like that on a test.
Yeah, I don't think, don't hold me to it, but I don't think you'll see that on your midterm. What about anything on this decibel scale right here, 64 through 70? Any questions on that?
I think you skipped that section. Yeah. We can go ahead.
Okay. All right, here we go. Okay, exponential and logarithmic equations. Does anyone want to see any of these worked out? All right, give me some numbers, guys. Nine. Okay. So we're going to do number 9. I'll do number 5, number 9, and then number 14 from this page. Okay, so I'll start with number 5 because it's the earliest one. 8900 equals e to the 5x. Well, it looks like the way you would want to do this is, let's rewrite it in log form. If you remember this equation, it's going to keep coming back. So b to the y equals x. And then that means log b of x, oops, equals y. So in this case, our b is e, our x is 8900, and our y is 5x. So that means when we're rewriting it, it's going to be log base e, we'll come back to that, 8900 equals 5x. Now log base e, remember, is natural log. So it's natural log of 8900 equals 5x. Oops. 5x. And then we need to get x by itself. So divide both sides by 5. And that just gives us x. Oh yeah, because we're just solving for x. Yeah. So x just equals that natural log of 8,900 over 5. You can put that in your calculator and simplify it if you want. It's going to be an ugly number either way, so I'm not going to write it out. All right. So I'm trying to write number 9 over here. We've got 8,000 equals 500 times 10 to the x. First things first, you can, if you have something out here outside of the parentheses, try and divide that out. So let's divide both sides by 500. I believe that's 8,000 divided by 500 is 16. Yeah, so we're left with 16 equals 10 to the x. All right, and there are 2 ways we could do it. Now we could put it back into the log form, like I did before. Or another way you can look at it is when you have, whoa, I don't know what that is. I don't know how to stop that. Okay. Another way you can look at it is we need to take the log of both sides. So just like how, we would subtract things from both sides, on this one, we'll just take the log of both sides. And that log, the base is going to match whichever number has the exponent. So it's going to be log base 10 of 16 equals log base 10 of 10 to the x. And remember, log base 10 can just be written as log. And then remember, with exponents, they can go out in front of the log. So it's going to be x times log of 10. And anytime these numbers are the same, it just equals 1. So x times 1 is just x. So we're left with x equals log of 16. Do those make sense? You could again, you could simplify that in your calculator if you want. I'm not going to run that right now. Okay, just use blank, I guess. Okay, I'm going to try and use these sticky things now, and I'm going to do number 14. Thank you. So we've got log base 4 of the cube root of 10. And we're going to be using this right here, the change of base formula. So let's go ahead and label our thing. So in this case, I'm going to zoom in. A is our base, so A equals 4. Ooh, actually, I'm going to, I could simplify this a step, couldn't I? I need your opinion on this, Ben. The exponent.
Yeah, I mean, yeah, I would write it as a 1/3.
Yeah.
Because it's prettier.
We can, I'm going to change this just a little bit to make it a little bit nicer. So cube root is the same thing as an exponent of 1/3. And then remember, with an exponent, we can take that. Did I left something out, didn't I? No, I didn't.
We're just doing change.
Oh, that's right. We're just going to change the base. Sorry, guys. Okay, so that's just 1/4. Or whoops, dude, I'm really having a rough time. Okay, so that's, you could have. Yeah, you don't need to do this step, but this is, a way to do it. So we're going to do change of base formula. So we're just going to focus. Oops. So now what we're actually working with is 1/3 log base 4 of 10. And we're just going to focus on what's inside of these parentheses right now for what's going to happen. The 1/3 will stay there, but we're not going to focus on it right now. That'll come back at the end. Okay. So again, our base is A, and in this case, that's specifically 4. And then our X is equal to 10. So now I'm going to use this formula right here. I'm just going to plug everything in with a new base. I'm going to use a new base of, is that? Yeah, I'm going to use a new base of 10 because the entire point is to be able to get this into either natural log or regular log. That way you can do it on any sort of calculator. Okay, so now this is 1/3. And remember, our new base is going to be 10. So I'm just going to write that out. So we're going to do log. And remember, if it's log base 10, you don't have to specify that it's 10. So log of 10 over log of 4. And then you would just plug that into your calculator. Does that make sense? Okay, cool. I know that was really long-winded. I'm sorry, guys. These logs are not easy, as I'm sure you all know. All right. Anything on this page that you guys want to look at? Okay, I'm gonna go ahead and move on to the next one. Would y'all like to look at one?
28.
Oh, 28. Okay. Let's see. Okay, we're gonna do 28. Start by rewriting it. 3 natural log of x plus 8. Natural log of 3x. Okay, so just like any other time we're trying to solve equations like this, we're going to try and get all of the natural logs on the same side. So first things first, I think I'm going to subtract 8 from both sides. So that gives us 3 natural log of x equals natural log of 3x plus 4.18. And now I'm going to subtract this natural log of 3x. Yeah. Subtract natural log of 3x from both sides. So we've now got 3 natural log of x minus natural log of 3x is equal to 4.18. And let's see if I'm making this harder on myself or not. Okay. Yeah, see that's, yeah. So now, before I move on to the next step, what can we do with an exponent? Or well, I just spoiled the end of that one. If we have a number out front that we're multiplying a log by, we can rewrite that as an exponent. And if you'll remember from earlier, anytime we have subtraction, we can rewrite that as one single division problem. All right. And now to get rid of a log, you remember a natural log is base e. You use that base right here and turn that natural log into our exponent. And you do that on both sides because anything you do to one side, you have to do to the other. And if you'll remember earlier, there was also a rule stating where if these bases matched, because remember that's net or log of e and this is e, then we can just cancel those out and it leaves behind this ugly mess. And we're still. Okay, yeah, we can do that. So now we've got, yeah, I don't like this problem, guys. This is an ugly problem. Good one. I'm glad you asked. Okay, so now we've got this here. I'm trying to figure out the next way to take this. What we have is x times x times x over 3 times x equals e to the 4.18. So we can cancel out one of these x terms. So now there's no longer going to be an x on the bottom. And we're left with x squared over 3 equals e to the 4.18. Dude, Araya, don't come back asking for help. This is too much. To cancel out something on the bottom of a fraction, multiply both sides by that. So we're just multiply both sides by 3. Cancel those out. We get x squared equals 3e to the 4.18. And then to get rid of a square root both sides. And that means we're left with x equals, yeah, I was gonna say, you know, plus or minus. Anytime we take the square root, you're left with a plus or minus of that ugly mess that I will let you type into your calculator on your own. But all right. Oh yeah, and don't forget, once you get that plus or minus answer, to plug them back up into the original equation and see if they still work. Spoiler alert, only one of them works. All right, so I'm glad that makes makes sense. That was torture. All right. Any other questions on that page? Because this is a big page of problems. If not, I'm going to move on to the next one.
Got 8 minutes remaining.
Yep. We've got 8 minutes left, guys. Okay.
So
All right.
ask
So,
them what they want to see on the last few pages.
okay. Is there anything on this page that you guys would want to look at? For 8 minutes. So we can go ahead and look through the rest if you want. Y'all can just try and keep track and tell me what problems you want to use. So, okay, I'm going to move on from this one. Oh God, constant percent change. Oh, I forgot what we're getting to. Oh man, it just gets worse.
Hey now.
Okay, so constant percent changes. Yeah, no. Yeah. This is just stuff that, you know, I haven't learned in a long time. You know, you're asking me to pull from the recesses of my mind. Anything on this page that you guys would want to look at? Sorry about that. Okay. What about these? Okay. What about these? Okay. Okay. First things first. We don't have any negative numbers in X or Y. So that means we can set up our graph to look just like that, just a coordinate one or a quadrant one, sorry. We got 1, 2, 3, 4, 5. 6. The beautiful thing about graphing in this class is you're sketching. You know, it doesn't have to be exact. And then we're only going up to 9. So I'm just going to count by twos, 2, 4, 6, 8, 10, just to make it clear what we're going up by. And then these are going up by 1. And now I'm just going to draw like a rough scatter plot here, okay? So 1 and 3.5, it's going to be like right here, 2 and 5.5, 3 and 6.8. Oh, hello, that brought up a magnifying glass. I don't know how that works. Okay, 5 and 8, and then 6 and 9. Okay, I know that's a rough little sketch, but I think it gets the idea across. Okay, so that's the idea of a scatter plot. And now this next part, I'm pretty sure you have to do this in your calculator. I could be wrong. Ben, can I get your opinion on that?
Yeah, I would definitely plug
Yeah,
in the calculator.
B through D. You're going to use those in your calculator. So what you do for that, I'm just going to write out some quick instructions. But you're going to press Stat, Edit, put your X's in L1, Y's in L2, and then you'll press Stat again, Calc, and then they're all three going to be labeled something different, but they are all on there. The first one's going to be, power. Let me make sure I have it in mind. Power reg, and then quad reg. And then, is it, which one? You tell me, Ben.
Logistic.
Okay, and then the last one is not labeled reg, it's just logistic. That's something that, you know, I don't really have a way to show you what it looks like on my calculator. If you have a calculator, I invite you to follow along. Did those steps make sense at least? I'm gonna assume yes, because I'm really killing this. All right.
We got 4 minutes.
All right. What about anything on this page? It's just more word problems working with exponential and log models. Okay. And then this one, just another word problem. Looks like a very wordy word problem. Whoops, skipped a page. Another word problem. One last word problem from the logs, and then we're getting into annuities and loan repayment. That's the exciting stuff. That's what you guys are here for. Anything y'all want to see from the beginning of 5.6? Let's see if I can do it. Okay. Any of these? All right. And any of these? Okay, so I'm going to go ahead and ask, are there any other questions throughout the packet that we might have sped past that you all might want to see? All right, if not, I'm going to throw it back to Dr. Blue.
All right. Awesome. So I just want to thank each of you for coming this evening and participating in our review session. It's always wonderful to have lots of people coming to do math, even if, Gavin has to whine about it. So as soon as this session is done, I will email all the participants, all the notes that we took on this packet. And I'll also post this to YouTube so you can watch the video link. All right. Thank you all and have a wonderful evening.